4-bit subtractor. We're going to label input output pins with the binary states that occur when subtracting. Let's do 13 minus 7. And here are the inputs and outputs. The bluish cyan color are the inputs we're going to apply, and the outputs are also listed out here on the right-hand side. So on the A string, we're going to have the number 13, the 8-bit, the 4, and the 1. I'm sorry, that was the 1. I got these backwards right there. There's a least significant bit up there. So that's the 1-bit, the 4-bit, and the 8-bit. And then here's the number 7, which is the 1, the 2, and 4. And since we're doing subtraction, we got to put the M in the 0 mode, which means we're going to be doing arithmetic. And then when you look at the function table, there's no such command as A minus B. The only thing we have access to is A minus B minus 1. So the fact that we're subtracting A minus B, and then we're subtracting another 1 from that, we're going to have to force a carry into this to make the answer come out right. Now, this carry, and when you put a 0 on here, that means you do have a carry in. And that's what we have to do to get rid of that A minus B, the minus 1 part of the A minus B. Okay, so here's all the S's, the mode control setup. We had to bring in the carry, and here's our 13 minus 7. Now, the answer for 13 minus 7 is supposed to be 6, and we will see 6 on the output. Since this is 2's complement subtraction, we will see a carry out of the most significant bit, which we always ignore. And the other 3 we'll just ignore. So these are the connections for that subtraction. So let's try a couple more examples. In example 724, I'm telling you what you're going to place on the input. So here's the A3, A2, A1, A0 is going to have that number 9, 1001 on it, and the B's will have that string, and the F's will be set up like that. We'll put the C in equals 1, which means no carry. And then we'll try it with the mode equal to 1, and then try it with the mode equal to 0. Now with the mode equal to 1, what would you see out there at the F's? So why don't you take a minute and try this yourself before I go and explain how this works out. Okay, so I assume you've tried this on yourself. Here's basically what I came up with. From the chart that you see in figure 727B, the logic function that we chose is the output of F will be equal to A ORed with the not B, with the complement of B. So what we do is we write down the A string, we write down the B string that we input, then we complement bit by bit, and then we OR this resultant, the complemented B string, or that with the original A string. So we have an A ORed with, or a 1 ORed with a 0, that's a 1. You take a 0 ORed with a 0, that's a 0. You take a 0 ORed with a 1, that's a 1. And finally, you take a 1 ORed with a 1, and that's a 1. So here is our answer. So that was using it as a logic device. Now, as an arithmetic device, you make the M equal to a 0. Now what would you see out of F? Well, when that's 0, the arithmetic operation is, from the table, it is A ORed with B, that's the logical OR, and then you take that result and you add to A. So first of all, you take the A, B, list them out, and you OR them. 1 ORed with 1 is a 1, 0 with a 1 is a 1, 0, 0 is a 0, and 0 with a 0 is a 1. And then we take that result and we add A to it. So if you take the A, the first bit is a 1, and you add that to the A or B bit, which is this, 1 plus 1 is a 0 with a carry. 0 plus 1 with the carry is a 0 with another carry. The carry comes around. The carry with 0, 0 is a 1, no carry. And then you come around, 1 plus a 1 is a 0 with a carry. So our answer on the F string is 0, 1, 0, 0. I hope that's what you got. So there'll be a couple more of these for you to try at the end of the chapter in the homeworks. And there's also 3 review questions in the textbook. So take a look at those review questions related to this, and then do the homework at the end of the chapter. So that completes section 7-10. Next, we'll take a look at using VHDL and LPMs to implement FPGA designs. That'll be section 711 coming up. I am Bill White. The materials that I'll be covering in this podcast is out of my Digital Electronics 9th edition textbook. I hope you find it useful. Hi, this is Professor Kleitz. In section 711, I'm going to talk about FPGA applications that are created using VHDL and LPMs. In this section, we'll duplicate several of the arithmetic circuits covered earlier in this chapter using FPGA implementation created with macro functions, and then we'll create them using VHDL, and then a new form of design entry that uses a built-in library of parameterized modules, LPMs. LPMs are provided in the core software to ease the design process for commonly used systems like adders and ALUs. So in the first example, example 725, we're going to build a block design file for a 4-bit adder using the macro function for the 74283 fixed function IC. So basically, Quartus has provided these what they call macro functions that duplicate all the internal wiring of the 74 series ICs. So that's what we'll do. We'll group the A inputs and B inputs and sum outputs as buses, and we're going to simulate different additions as you monitor the results from the sum bits and the carry out. So I'm going to run the Quartus software now and I'll show you how to build this macro function. Okay, so here's the Quartus software, and normally you'd go through the File, New Project Wizard, and go through, File, New Project Wizard, and go through the steps and naming your project and going through all the steps that we followed back in Chapter 4. Eventually, you'll get to the part where we have a new block diagram schematic file. So that's the part I want to talk about. So to create the macro function for that 74283, you right-click, insert, symbol, And as you type in 74 283, it finds that there's a whole series of macro functions available. We'll say OK to that, and we'll drop it somewhere here on the screen. Next thing you want to do is line up the inputs and outputs. So if you right-click, insert symbol input, and we'll drop that right here. And as soon as you name the input, we're going to do the A string. So we'll call it A, and it's the bracket 3.0 end bracket. OK. And I get the right bracket here. Yeah, the square bracket. And as soon as it does that, it knows that this is going to be a bus line because it's a vector with 4 elements in it. And as soon as I drag the line, it realizes that it's a bus, and it makes it the correct thickness for a bus line. But these are individual scalar quantities. When I hook them up, it thinks they're a bus also. And we're going to show you how to fix that. Oops, I went a little too far in there. And then I'll hook up the A3 line, and then I'll hook up the A4 line. And it thought the A4 line was also a bus line. Now, if you right-click, point to the line that you want to change, right-click, and say a node line, because it's really just a node line. It's a single scalar quantity feeding into a bus line. And then right-click here, same thing, select node line. And they both got created as node lines. Now, we have to break these lines out individually. So this is really the A1 line, the A2 line, and so on. So if you right-click on the line and select properties, and then give it the name, A, square bracket, 0, end square bracket, and hit OK, it labeled that line as the A0 line, and we do that for all 4 of these. I'm sorry, that's the A1. I should have said A1. I typed that wrong, so I should say A1, A2, A3, and A4. And then we have to do the same for the Bs. Okay, so I changed A1, and you can also bring it down closer to the line because we're going to get a little crowded here. So I can bring these down a little bit closer. And then continue with A3 and A4. Now let me show you how to do the B line. So again, you say insert, input, symbol, input. That's already available, and drop it. We'll drop it right there. And the pin name is going to be B, bracket, 3.0 bracket. And same thing with this. When you go to hook it up, it's going to think that it's a bus, and it draws a bus line. That's fine. But B4, we're going to have to change that. B3, they figured that. It's got that one. Oh, I dropped that a little bit too low. Let me see if I can just erase that. Right up there we go. Oop, that connection got broken. And the B1, I'm still not up high enough. Go up a little higher. And bring the B1 over. And then I'm going to right-click on the B1 and make sure I call that a node line. Right-click on the B4, make sure it's a node line. And let me just label the last one here. So I right-click, and I say properties, which is off the screen a little bit, but the properties are going to be B, and this was B4, I think, is where I was. And there it is. Bring it down a little bit lower, and then B3, and then B2, and then B1, and so on. You're going to do the same thing with the sum outputs. They're also going to be, and I'll just show you how to do an output. So you right-click, insert symbol, outputs, and we'll put that right there. And this also is going to be a bus line for the 4 sums. Oh, it didn't know it was a bus line because I didn't name it a vector first. So if I name that first, let me highlight that, hit the delete key, and name this first. And what are we calling it? Sum bracket 3.0 end bracket. And now when I draw this line, it'll know it's a bus line and draw it that extra thickness. And then I'll connect up the node lines. Oh, and these connected up. It knew these were nodes. Looks like that first one didn't connect. That's why. Okay. And then we'll have to right-click, node line, right-click, node line, and then label these lines. So here, right-click, properties, sum 3. Oops. I'm supposed to make that sum 1. You can double-click. You can actually get into a typing mode here. I can say, put the 1 in that way, and then sum 2, sum 3, and so on. Then CL is just going to be a single output. So when you label, and I'll show you how to do that. So again, you right-click, insert symbol, output. It's all ready to go. And we'll drop that right here. And that's going to be called Cout. And that's just going to be a node line. When you hook that up, it hooks up directly as a node line. And then we got to do the CN also. And then we're going to create waveforms for the CN, the A string, and the B string. We'll look at the sum and output. So let me show you the final designed circuit. And here's the final circuit design. And we've got the Cout, and here's the CN, which is grounded. We're going to be looking at the sums. I have these all as defined as node lines, and then we have a bus line. We got a bus line for the B, we got a bus line for the A, and then we have the individual node lines labeled. And then next, I created a vector waveform file, and I set A up as a series of numbers, and I just made up some numbers, 3, 2, 6, and I want to try to add these together. So we're actually going to be adding 3 plus 6, 2 plus 4, 6 plus 6, C plus 2, and so on, and we'll be looking at the sum and carry out. And if you need a refresher on creating a vector waveform file, go back to Chapter 4. So to run the simulation, we'll use a shortcut key, and the simulation waveform is created successfully, and here are our waveforms. So as you look at these, it sure did work fine. So we got 3 plus 6 is a 9, that's correct, no carry. 2 plus 4 is a 6, 6 plus 6 is a C, and so on. Now we get up into the carry out. D plus 4, D is really a 13. 13 plus 4 is 17. That's 1 over the 16, so the answer is 1 with a carry out. 9 plus 9 is 18. That's 2 with a carry out. A plus A is 10 plus 10 is 20, is 4 larger than the 16, so that's 4 with a carry out, and so on. So this macro function was a quick way to come up with a 4-bit adder based on the fixed function 74283. Okay, in the next podcast related to this section, I'll show you how to develop your own VHDL program from scratch to do the same thing. Hi, this is Professor Kleitz. We're still working in section 7-11. And in this example, 7-26, we're going to design an 8-bit adder subtractor, so we'll be able to do both addition or subtraction. We'll be doing the design in VHDL using the plus and minus arithmetic operators. Back in figure 720, we use integer data types for performing arithmetic. When the answer track is 0, else you do a subtraction. How much simpler could it be than that? So here's how we're getting to see our when-else conditional assignment. So let's look at a simulation of that. And figure 732 shows the simulation results.